Hello friends. So as we have understood the concept of the momentum equation in hydrodynamic boundary layer, so by that momentum equation we have found the velocity profile inside the hydrodynamic boundary layer. So similarly, because there is also formation of the thermodynamic boundary layer or thermal boundary layer, so we'll also find here the energy equation for the thermal boundary layer, and by applying that energy equation, we'll try to find out the temperature profile inside the thermal boundary layer. So first of all, let us suppose a thermal boundary layer on a flat plate. Let's say we have a thermal boundary layer on a flat plate. This is the free stream temperature, T infinity. This is x direction, and this is y. This is xy axis. Fine. And let's say we have taken a temperature profile like this, and the temperature gradient will be del T del Y. And let's say we have a wall temperature is TW. Heat flux is going through this direction. So to derive the energy equation, let us suppose the fluid element here. And what are the energy interaction inside this fluid element? We'll try to understand that uh, because some energy is entering here and some is going out from here. Fine, that heat and some is going from this direction and some is going outward direction. Uh, if I talk about the energy interaction in this fluid element, so there are two types of energy interaction will be there. First is because of the convective effect, because of the convection of the heat that I have shown with the green color, and there is one more interaction, heat interaction, that is because of the conduction effect of the fluid that we can show like this. That heat will conduct from this layer to this layer because actually the layers are more likely to be static layer by layer. So heat will not convect directly from the bottom layer to upper layer. It will conduct as well as convect. Fine. So I mean the conduction is more towards y direction. That's why we have to consider. So like the hydrodynamic boundary layer, we have there are also assumptions in the case of the thermal boundary layer. So what are the assumptions? Let's try to find out. So the first assumption will be the flow is taken to be steady, 2D, and incompressible flow. 2D means what? The u velocity is function of x and y. The v component is also function of x and y, and the temperature will be also function of x and y, which we want to find out the temperature profile. So here one more thing we have to keep in mind that temperature gradient with respect to y is much greater than temperature gradient with respect to x. It means that the change of temperature in y direction is more than the change of temperature in x direction. So here the temperature is a strong function of y and very weak function of x. Right? The second assumption will be that heat conduction along x direction is taken as or negligible negligible heat conduction along x direction. Third is what? We have assumed constant fluid properties. Four is what? We have assumed unit depth perpendicular to the plane of figure. These are the assumptions. Now, let us take this fluid element here and try to find out the different heat or energy interactions. So first, I'll show the convection. Let's say along x direction. Is this here? The heat is convecting from x direction, so that we can take it as uh, that rate of change of mass Cp into rate of change of mass Cp and T. This is the rate of change of the energy which is entering inside this fluid element. Or in other words, in terms of the density into area dy into 1, because this is dx and this is dy into u cpt. So what will be coming out of the here? Let us directly m dot cpt. We can directly if I will try to write in terms of mass only, then I will write it like this: m dot plus del m by del x dx cpt, or in terms of rho, I can write rho dy into 1. Then u is changing with respect to dx, u del x to dx cp, and t is also changing, so that is t plus del t upon del x dx. This is the heat convected outward, and heat is convecting from bottom direction. This will be rho dx into 1 dx into 1 into v cpt. So what will coming out? That will be rho dx into 1 into what we have written v. V will change del v with respect to y dy cp, and t will also change with respect to y dy. This is the heat convected. Now, one more important thing, that heat will also conduct along y direction. So the heat conduction will be according to Fourier's law, k into area dx into 1 into del t upon del y, and it will come in like minus k dx into 1, and the rate of change, the gradient of change, that is del t upon del x is already there, so it will change with respect to uh, y only, del by del y, del t upon del y, oh, so, and dy. This is the heat conductor. Fine. So this is our, what is that? Control volume. We have equated all the energy interactions. Now, if we'll try to manage all the equations, we'll balance all the equations. So what we can see that the thermal energy or enthalpy transported or convected by the fluid is written as m dot cpt. This is what? This is the energy, thermal energy transported, or the enthalpy transported or convected by the fluid. Okay, or I can write it like this: enthalpy transported. This is the enthalpy transported. So we can, if we'll balance all the equations, so we can say that the heat convected through the bottom phase plus heat convected through the left phase plus heat convected through the bottom phase. It means that uh, let us show you. If I'll show you, So what are the heat is coming inside? This is the heat coming inside. Heat coming inside. This is what heat convected from the left face, and this is the heat convected from the bottom face, and this is the heat conducted from the bottom face. And what are the what heats are going out? That is that is heat convected from the right face, heat heat convected from the top face, and heat conducted from the top face. These blue and green heat is balanced, that will be balanced. So if we'll try to compare the heats or the energy transported, then we'll get the final energy equation. So what will we get the final energy equation? That we will get like u del t by del x plus v del t upon del y is equal to k upon rho cp del square t del y square. This is the energy equation inside the thermal boundary layer. So we can say that the net heat converted into the control volume, net heat converted into the control volume is equal to net heat conducted conducted out of the control volume. Or if we'll define that K upon rho Cp is called alpha, that is thermal diffusivity. So we can write that U del T by del X plus V del T upon del Y is equal to alpha del square T del Y square. So this is what? This is the energy equation. Energy equation. And what we have got in the case of the hydrodynamic boundary layer, we have got the momentum equation. And what was that? That was u del u by del x plus v del u by del y is equal to nu. That is the kinematic viscosity is equal to del square u by del y square. So you can see that the both equations are very much similar. Very much similar. If the nu and alpha will equate, I mean maybe same, then the both equations are most likely similar. So there is a striking similarity between the momentum equation of hydrodynamic boundary layer and the energy equation of the thermal boundary layer. The solution to both these second order differential equations would exactly be the same if kinematic viscosity mu of fluid is equal to the thermal diffusivity alpha. Fine.